Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Synthesis of Nanostructured Materials under the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, the classification of nanoparticle synthesis techniques is described and the pressure-temperature mapping is discussed. In this module, gas phase condensation process is studied in detail along with the schematic setup. Then, the chemical vapor synthesis method is studied in this module. Finally, advantages and disadvantages of gas phase condensation technique are discussed in this module. The inert gas evaporation condensation processing wherein nanostructured materials are produced by the evaporation of a metal source in an inert gas is an extensively employed technique to synthesize very fine metallic particles or nanoparticles since 1930s. This synthesis protocol has been followed for producing crystalline nanoparticles in powder form. These nanoparticles can be consolidated in situ into small disks under ultra-high vacuum conditions. Since long time, this processing is known to produce very fine-grained or amorphous alloys depending on the substrate temperature and other operating conditions. Let us discuss about the synthesis of nanostructured materials. The growing appeal in nanotechnology is owing to size-dependent properties which are demonstrated by the nanostructured materials. Nanostructured materials or nanoparticles principally are the materials whose at least one dimension, that is, grain size, layer thickness, etc., is in between 1 and 100 nanometers. Size and morphology control are the most imperative parameters to be taken care during the formation of nanoparticles having desired properties. Though the size of a nanoparticle plays major role in the sensor, biological and catalytic applications, shape or morphology control is also significant because of the novel application in sensors, optoelectronics, photochemistry and fuel cells. Furthermore, other concerns to be considered include the monodispersity, agglomeration, and surface functionalization. Consequently, a wide range of synthesis techniques have been devised for obtaining high-quality nanoparticles which can be categorized as mechanical methods, gas phase methods, and liquid phase methods. The mechanical methods include processes such as grinding, milling, etc. The gas phase processes includes the chemical vapor deposition, laser ablation techniques, or the physical vapor deposition techniques, etc. The liquid phase methods includes techniques such as hydrothermal synthesis, sol-gel fabrication, etc. Figure 2 shows a map of the temperature and pressure values which are required for various synthesis processes. We can see that a process like evaporation undergoes processing at low pressures and a temperature of around 1000 degrees centigrade, where the sputtering takes place at slightly higher pressures but at lower temperatures. Plasma formation takes place at a very high temperature of around 2000 degrees centigrade. Similarly, as we move towards other processes, liquid phase methods such as CVD, hydrothermal, solvothermal method, the pressure keeps on increasing. The Sol-Gel method takes place at a high temperatures of around 1000 degrees centigrade and high pressures of 10 raised to the power 5 Pascal. In this module, we will learn about the basic principle and applications of gas phase condensation technique and vacuum deposition methods. Let us discuss next about the gas phase condensation. Gas phase condensation processes are one of the oldest methods for materials processing and have many advantages over other nanoparticle synthesis techniques. Gas phase condensation is a bottom-up protocol for producing nano-sized material. They provide the capability to precisely control the process parameters to produce nanostructures with preferred morphology along with desired chemical composition. These synthesis techniques are based on homogeneous nucleation in the gas phase and subsequent condensation and coagulation. Over the years, numerous improvements in the gas phase condensation process have been devised, resulting in different synthesis methods. Nonetheless, the basic working mechanism for all these techniques is the same and can be summarized as follows. First one is suspending the target material in gas phase. Secondly, conversion of the target material into small clusters. Third, enforcing the growth of these clusters to nanoparticles. And fourthly, collection of synthesized nanomaterials. Gas phase condensation process utilizes an inert gas at pressures sufficiently high to promote particle formation, but low enough to allow the production of spherical particles. Gas phase condensation employs a vacuum chamber, which includes a heating element, the metal to be converted into nano powder, powder collection apparatus, and vacuum hardware. Metal is introduced onto a heated element and is rapidly melted. The metal is quickly taken to temperatures far above the melting point, but less than the boiling point, so that an adequate vapor pressure can be attained. Gas is continuously purged through the chamber such that the gas flow moves the evaporated metal away from the hot element. As the gas cools the metal vapor, nanometer-sized particles form. These particles are liquid since they are still too hot to be solid. The liquid particles collide and coalesce in a controlled environment so that the particles grow to specification, remaining spherical and with smooth surfaces. As the liquid particles are further cooled under controlled conditions, they become solid and further growth of the particles is stopped. At this point, the nanoparticles are very reactive and possess strong attractive forces among themselves. As a result, these particles tend to agglomerate to form clusters. To prevent the agglomeration of the particles, they are generally coated with a protecting material which prevents their interaction with other particles or with other materials. Figure 3 shows the schematic of setup which is used for gas phase condensation technique. As can be seen in the figure, the setup comprises a vacuum chamber which is attached to a furnace. It has a target material, condensation mechanism, and vacuum hardware. Once the target material vapors are supersaturated, they condense to form the desired nanostructures. The condensation is carried out by either physical or chemical process. Gas phase condensation is the most preferable technique for synthesizing metallic nanostructures. Metallic materials exhibit reasonable evaporation rates at practical temperatures. A typical gas phase condensation process is carried out under inert atmosphere. However, to enhance the reaction rates, reactive gases can be introduced into the reaction chamber. These reactive gases help to form metal oxide and metal halide nanoparticles. The dimensions and morphology of these nanoparticles can be controlled by the evaporation rate, rate of condensation, and the gas flow. This process is different than the vacuum evaporation technique in the fact that the vaporized atoms spend their kinetic energies rapidly in an inert gas in the collisions with the atoms of the gas, thereby forming clusters of the atoms or the nanoparticles. In other words, this process can be summarized as nanoparticles are formed when vapors supersaturate in the condensation region. We next discuss the factors which controls the synthesis of nanoparticles in gas phase condensation process. The factors controlling the synthesis of nanoparticles in gas phase condensation process are firstly the rate at which atoms are supplied to the supersaturation zone so that condensation may occur. Secondly, the rate at which the condensing medium, that is, the inert gas flown into the reaction chamber, removes the energy of the hot atoms. Third, the rate at which the produced particles or clusters of atoms are removed from the supersaturation zone. One more type of gas phase condensation technique is chemical vapor synthesis, in which chemical vapors of precursors undergo reactions in the reaction chamber. Temperature of the chamber is raised by Joule heating. This technique is identical to the chemical vapor deposition technique, with the exception that instead of thin film deposition, this technique produces nanoparticles. The resident time of precursors inside the chamber is a crucial parameter which decides the structure of the particles. The target material can be in solid, liquid, or gaseous phase at ambient temperature. Let us next discuss about the chemical vapor synthesis. Chemical vapor synthesis technique can be summarized as: first, the precursors are heated to form vapors. Then the precursors vapor are carried into a hot wall reactor. The conditions in the reactor are such maintained that the particles nucleate in the vapor phase. In this way, any film deposition on the walls of the reactor is prevented. This technique is analogous to the chemical vapor deposition technique and is also described as chemical vapor condensation. It differs from CVD in the manner that CVD is employed for depositing thin solid film on the surface of a substrate. This process can be used to produce an extensive variety of materials. Additionally, being analogous to the CVD technique, it benefits from the wide range of precursor chemistries introduced for the CVD technique, because all of them can be applied to this process as well. In ambient conditions, the precursors can be solid, liquid, or gas. However, they are taken into the reaction chamber in vapor form. The vapors can be produced from a bubbler or sublimation source. Figure 4 shows the schematic representation of the experimental setup which is employed for CVS method. In a typical CVS process, metal organic precursor is inserted into the hot wall reactor at a controlled rate. For producing halide, nitride, carbide, or metal oxide nanoparticles, the reaction chamber is filled with respective reactive gas precursors. If a mixture of gas reactants is introduced in the reactor, the energy which is produced from resident heating, laser, or plasma heating can cause chemical reactions among them. For producing oxides, chlorides are the most popular precursors owing to their characteristically low vaporization temperatures and low cost. A common chemical reaction which is taking place inside the reactor involving chlorides is as follows: SnCl4 in gaseous phase plus 2H2O in gaseous phase will give SnO2 in solid phase plus 4HCl in gaseous phase. The chemical vapor processing or the CVS method can also be used to form doped or composite nanostructures. This is achieved by introducing multiple precursors into the reaction chamber during synthesis process. In this method, the second precursor is supplied to the reaction chamber at a later stage. This technique can also be used at commercial scale. Various types of oxide nanostructures have been produced by this method. We will now discuss some of the most popular oxide nanoparticles which are produced by chemical vapor synthesis technique. Nano-sized particles of the oxides of indium, tin, and tin oxide doped indium oxide are synthesized by chemical vapor synthesis for their application in transparent conducting oxides, catalysts, as well as sensing devices. These nanopowders demonstrated a narrow size distribution with an average size of approximately 5 nanometer. Lately, semiconducting nanobelts or nanoribbons of binary oxides have been fabricated via evaporation and subsequent condensation of the precursors. Examples include the nanobelts of zinc oxide, In2O3 indium oxide, gallium oxide, cadmium oxide, etc. Precursor was used in powdered form and was vaporized inside a tubular furnace at high temperatures. The vaporized precursor was made to supersaturate and then condense in controlled conditions, that is, temperature, pressure, substrate, etc. Such controlled condensation of the precursor vapors lead to the formation of desired product. The as-synthesized oxide nanobelts were pure and exhibited structural uniformity. These nanobelts were single crystalline and defects and dislocations were almost non-existent. All of them had rectangular cross-sections having width between 30 to 300 nanometer, width to thickness ratio between 5 and 10, and lengths around few nanometers. All the semiconducting oxides exhibited belt-like morphologies. Semiconducting nanobelts are ideal systems which are best suited to appreciate the effects of dimensional confinement on the transport properties of advanced functional oxides. Such understanding of transport properties is essential towards fabricating functional devices comprising single nanobits. Figure 5 displays both the high and low magnification pictures of as-synthesized zinc oxide nanoring which is obtained from scanning electron microscopy. Since the zinc and oxygen terminated basal planes in zinc oxide respectively possess positive and negative ionic charges on them, a spontaneous polarization is induced in them, and the direction of this polarization is normal to the surface of nanobelt. Consequently, helical nanosprings or nanocoils can be produced by simply rolling up individual nanocrystalline belts. This helical growth is attributed to the minimization of total energy resulting from spontaneous polarization and elasticity. Owing to the polar surfaces, zinc oxide nanobelts and helical nanosprings are ideal structures to understand nanoscale piezoelectricity and polarization-induced ferroelectricity. Additionally, the metal oxide nanostructures such as nanobelts, nanowires, nanoribbons, etc. are potential candidates for various sensing applications. We can see in the figure that the diameter of the ring was found to vary between 1 micron and 4 micrometer. Ring thickness varied between 10 nanometer and 30 nanometer, and width of the ring shell is about 0.2 to 1 micron. The quantity and quality of the produced oxides depends upon the reactants as well as the temperature of the reaction chamber. Let us next discuss the advantages of the gas phase condensation technique. The various advantages of the gas-phase condensation technique are: firstly, coatings can be produced by directly precipitating nanoparticles from the gas phase to the surface. Secondly, this technique can produce oxides at relatively shorter residence time. Third, the technique can be easily scaled up for bulk production. It can produce highly pure products. Handling of continuous processes is easy. Also, the temperature stability of the products in the gas phase condensation technique is high. Let us next discuss about the disadvantages of gas phase condensation technique. The products required for the gas phase condensation technique, which are to be separated from the gas stream, have relatively high volume. Good filters are often required to do the job. Secondly, the process required highly pure precursors, which may be expensive, as purification during the synthesis is not possible. This technique cannot be used to produce porous materials because of high temperatures. Also, another disadvantage of the gas phase condensation technique is that this technique produces nanoparticles which are tightly agglomerated and require further processing to disperse these nanoparticles. Monodispersed products can also be produced via condensation or surface growth mechanisms. The residence time as well as the temperature profile of the reactor is not uniform. So students, let us now summarize what we have learned in this module. In this module, the classification of nanoparticle synthesis techniques was described and the pressure temperature mapping was discussed. So students, let us now summarize what we have learned in this module. In this module, the classification of nanoparticle synthesis techniques was described and the pressure temperature mapping was discussed. Also, the gas phase condensation process was studied in detail along with the schematic setup. Then, the chemical vapor synthesis method was studied in this module. Finally, advantages and disadvantages of gas phase condensation technique were discussed.